So section 10.3 is our next section. And this one's going to have actually several theorems in it, but they're all related to each other. So if you pick up on the relationship, knowing the theorems will not be a problem at all. And so we're going to start off talking a little bit about the anatomy of a circle. There are different parts and pieces that we're going to look at. And we're going to also bring in some angles into our circles. So this is called 10.3 arcs of a circle. Arcs of a circle.
I need to get the app, so
that would be my son getting an app for something. I'm not sure what. Okay, so we need a circle. Here's our circle. And this point right here is the center. All right, Mrs. Carty, this is not very challenging yet. Let's put 2 points on our circle. Let's call them A. And we'll put a point over here. We'll call him B, and then we'll come around and call this one C. And the center, we'll name it circle O. Okay, so this right here, A to C, is called a minor arc. A minor arc. And you're saying, that's nice. So what's a major arc? Well, the major arc is going to be from A to C, but it's going through B. So your major arc is this guy here. So the major arc goes all the way around this way. So major is big, minor is small. All right, so let's say we draw in our radii here, O to C and O to A. And so that creates an angle. And this angle, since the vertex of the angle is located in the center of the circle, it's called a central angle. So any angle whose vertex is in the center of the circle is a central angle. All right, I'm going to draw a diameter across. So here we go. Drawing in a diameter. So this arc that shows up because of the diameter is called a semicircle. You probably already knew that. Semicircle. Half the circle. Okay. So you remember that the number of degrees in a circle, there are 360 degrees in a circle. We can talk about an angle in degrees, but we also talk about the measure of an arc in degrees. So there's a difference between the measure of an arc versus the arc length. So the measure of an arc, it's an angular measurement. So it's going to be in degrees, right? Arc length is a linear measurement. So that'll be in like centimeters, miles. So it's units to the first power. So let's look at an example. Oh, sorry, I was falling off the page there. Linear measurement. All right, let's look at an example. We have a little circle here, and we'll call this circle P. And we're going to put in a central angle, AB. I'll put C over here. So here's our picture. And let's say that we know the measure of arc AB, that's how we say arc AB, is equal to 20 degrees. Find the measure of arc ACB. So AB is this minor arc, it's 20 degrees. We want to find the measure of arc ACB, so the major arc. So we just need to make sure we understand the relationship here. The whole thing is 360. 20 is taken up by AB. So what's left over is ACB. So that's 340 degrees. All right, let's look at another example. I'll just draw a line here because it's not going to be a big example. Let's say we have this circle here, and this is circle Q, and we've got X and Y, and this is D. And let's say that the measure of arc XQY, I'm sorry, not the measure of the arc, the measure of angle XQY equals 110 degrees. 110 degrees. We're going to find the measure of arc XDY. So angle XQY is 110 degrees. That's the angle right here. We want to find the arc XDY. Well, if this angle is 110 degrees, guess what this arc measurement is? It's also 110. The central angle and the measure of the arc are exactly the same. So the central angle and this arc here are exactly the same measurement. So this is called, what's called here, this is called the intercepted arc. And it's intercepted, meaning it's being created by an angle cutting it out. So the intercepted arc equals the central angle. They're the same measurement. Oh, sorry, you didn't see intercepted arc. There we go, intercepted arc. And that's equal to the central angle. Back to our example. If this is 110, we want to find this major arc here, XDY. So remember, there's 360 degrees all together. We will take off the intercepted arc, which means we are left with 250 degrees for XDY. Not too bad, right? Okay, let's talk about something else. Let's look at congruent arcs. We're going to definition of congruent arcs. All right, I want you to open your textbook. You're going to open your textbook up to page 452. 452. Wish I had music that I could play you while you're doing this. Dun, 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 dun. Okay, everybody got it? 452. So look at where it says congruent arcs in the middle of the page. It's big, it's red, it's larger font. Okay, congruent arcs. And read it while I read it. Two arcs that have the same measure are not necessarily congruent arcs. In the concentric circles shown, the measure of arc AB is 65 and the measure of arc CD is 65. So that's their degree measurement. But arc AB and arc CD are not congruent. So they're linear measurements. If you were a little bug walking along, you would want to be the bug walking on CD because it would go faster. It's shorter versus the arc AB. So they do not have the same linear measurement. So the question asks, under what conditions will the two arcs be congruent? So look under the definition there. Two arcs are congruent whenever they have the same measure and are parts of the same circle or congruent circles. So they have to be parts of the same circle or congruent circles. And they have to have the same measurement. So parts of the same circle or congruent circles and have same measure. Okay. So let's put that aside for just a second. We're going to talk about this picture here. Circle with a center. We'll call this center O, and we'll draw a radius here, and we're going to draw a radius here, and we're going to draw a radius here, and then we're going to do one here, like so. So we're drawing triangles, these two little triangles, looks like a little bow tie kind of. This is AB, this is CD. All right, so there are three things that we know to be true, or there's three theorems that we're going to show are true. So first of all, we have to first state in the same or congruent circles. So we first need to make sure we have this premise met, that we are either in the same or congruent circles. In this case, we're in the same circle. If that is true, then if the chords are congruent, so if we have congruent chords, then we have congruent arcs. I'm going to do a little arrow like this. Here we go. Then congruent arcs. Likewise, if we have congruent arcs, then we have congruent chords. So this arrow can go both directions. So let's speak specifically to this particular situation. Congruent chords would be AB is congruent to CD, straight lines, right? Congruent chords. If that's true, then the arcs are congruent. So arc AB is congruent to arc CD. Likewise, if we know that arc AB is congruent to arc CD, then chord AB is congruent to chord CD. So guys, you just knocked out two theorems right there. There's 6 theorems to do today, but you've just done 2 at a time. Let's do another set. If the arcs are congruent, then the central angles are congruent. Likewise, if the central angles are congruent, then the arcs are congruent. So again, let's do our particular here. Congruent arcs, so that would mean that if we know arc AB is congruent to arc CD, then angle AOB is congruent to angle COD. Angle AOB is congruent to angle COD. Likewise, if we know that angle AOB is congruent to angle COD, then arc AB is congruent to arc CD. You've just knocked out 2 more theorems. Let's do the last set. Guess what? Let's do the combination we haven't done yet. So in this case, we have congruent chords If we know that the chords are congruent, then we know that the central angles are congruent. All right, so getting specific now with our particular here, congruent chords. So we would need to know that if AB is congruent to CD, then angle AOB is congruent to angle COD. Likewise, if angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. So there's 6 theorems here, but they're all related to each other. So keep this handy while we do the examples. Here we go. Example number 1. Let's do this little proof here. So we are given circles P and Q. We know that angle P is congruent to angle Q, and AR is congruent to RD. That's our given. We're going to prove that arc AB is congruent to arc CD. We need a picture. So I'll draw this. There's 2 circles, that one and that one. There's the centers. This is circle P, this is circle Q. And then we're going to do this. All right, and then our points here, this is point A, this is point B, this is C, this is D. I'll give you a second to catch up on that. Again, I wish I had music. What song am I thinking of right now? Name that tune. What is it? Anybody? No? You haven't been watching enough TV yet. I Dream of Jeannie. Okay, here we go. There's a little hint to this one. Okay, I'm going to give you a little hint. Whoop. Hint. Show congruent circles first. Circles first. Because once we have congruent circles, then that means our 6 theorems are in play. We can utilize what we need there. So here we go, congruent circles. Well, if the circles are going to be congruent, that means that their radii need to be congruent. So let's think about this. We have angle P is congruent to angle Q from the given, and we have that AR is congruent to RD. All right. Well, since angle P is congruent to angle Q, look at our triangle here. That would mean PR and RQ are congruent. Pardon me. So since angle P is congruent to angle Q, then RP is congruent to RQ, because if the base angles are congruent, then pardon me, it's very dry today. It's actually not raining. Okay, so then we know this piece here is congruent to this piece here. Well, if those guys are congruent and AR and RD are congruent, then hey, wouldn't that mean that AP and DQ are congruent by subtraction? So by subtraction, AP is congruent to DQ. Thus, circle P is congruent to circle Q, since the radii are congruent. All right, so now we have congruent circles. Now let's keep in mind, we want to show that AB is congruent to CD. So AB is here, CD is here. What are these kinds of angles called? Those are called central angles. So we're in the same circle or congruent circles. We're in congruent circles in this case. If these central angles are congruent, where am I? There we go. If the central angles are congruent, then the arcs are congruent. Well, that's what we want. So AB, arc AB, is congruent to arc CD, since if central angles congruent, then arcs congruent, or intercepted arcs are congruent. Okay, so there's an example. All right, let's do another example. Let's do this guy. Let's do another proof. Here we go. We are given circle B, and D is the midpoint of arc AC. We are going to prove BD bisects angle ABC. Okay, keep in mind, BD bisects angle ABC. What does an angle bisector do? Cuts it into two congruent angles. So keep that in mind. We're going to have to show two congruent angles. Here's our picture. Circle, this is circle B, and here is A, D, and C. There's our picture. All right, D is the midpoint of this arc. Well, where is a midpoint located, people? In the middle. So what do we know about AD and DC? They're going to be congruent, right? So since D is the midpoint of AC, then arc AD is congruent to arc DC because a midpoint divides an arc into two congruent arcs. Okay, so this guy is congruent to this guy. All right, we are in the same circle. We have congruent arcs. So let's go back to our theorems from today. If the arcs are congruent, then the central angles are congruent. So we can say angle ABD is congruent to angle DBC, since if arcs congruent, then central angles are congruent. Therefore, BD bisects, oh here, let me mark my picture too. There we go. BD bisects angle ABC since it divides the angle into two congruent angles. There we go. That's not so bad. All right, let's do a couple of algebra-ish problems, and we'll call it quits. This has been a little bit longer, so I apologize. All right, example. Here we go. Here's our circle. This is circle O, and we've got this angle here. We know that the measure of arc AB equals 102 degrees. Find the measure of angle A and the measure of angle B. And I forgot a line that is very important in this picture. There. Okay, we've got 102 for our angle, or pardon me, our arc. 102 degrees for our arc. So this angle right here is worth how much? I hope you said 102. So this angle is worth 102. So now let's hone in on this triangle. What kind of a triangle is that? Well, OB and OA are radii. Radii in the same circle are congruent. So what kind of triangle is that? Isosceles. So those angles, those base angles should be congruent. If I have 102 degrees taken up by this angle, what's left over? Well, 180 minus 102 leaves us with 78. And then we have to divide it evenly. So each of the little angles gets 39 degrees. Okay, here we go, last one. What fractional part of a circle is an arc of 36 degrees? So keep in mind, we're talking about degrees. Fractional part is just a ratio. We're comparing two things. We're comparing this part with the whole. So if the part is 36, what's the whole of a circle? 360. So reduce your fraction. Your ratio or your fractional part is 1/10. What if you had a 200 degree arc? What would be your fractional part of the circle? So we've got 200 over 360. Reduce your fraction. You have 5/9 of a circle. So then let's work backwards. Find the measure of an arc that is 7/12 of its circle. All right, there's a key word in here that tells you what to do. Of. Of in math means multiply. So we've got 7/12 of a circle. What's a circle worth? 360 degrees. So you multiply it together, do a little cross canceling, 210 degree arc. All right, so there you go. That's section 3. Work on some of the problems and I'll meet you in our Zoom in a little bit.